I want you to imagine you're driving a car. You're on a steep highway, maybe coming down a mountain pass. You're going a little too fast, so you tap the brakes. Nothing. You press harder. Still nothing. You aren't just speeding, you are accelerating, and the mechanism you rely on to slow down has fundamentally disconnected from the wheels.
That is a terrifying image. And unfortunately, it is the exact analogy we need for what we're covering today.
It really is. I was reading this article in Above the Norm News this morning, and, usually when we talk about climate change, we talk about the gas pedal, right?
Right. Emissions, fossil fuels.
How much carbon we're pumping into the air. But this article, it just flips the script. It suggests we are completely ignoring the brakes.
It's a classic case of focusing on the input and ignoring the output. The article, it's based on a new study from Communications Earth and Environment.
Okay.
But the Above the Norm News interpretation takes the raw data and asks a much, much scarier question.
Which is?
What happens when the Earth's natural safety systems just stop working?
They call it feedback failure. And honestly, reading through it, it felt like the script of a horror movie where the call is coming from inside the house.
Yeah.
We aren't just looking at how Earth heats up, but how it loses the ability to cool itself down.
And that distinction is just, it's vital. We tend to think of the Earth as this passive backdrop that just, absorbs whatever we throw at it. But it's a dynamic, reactive system. It has thresholds.
And this research suggests that when you cross those thresholds, the planet doesn't just get warmer, it switches into a completely different operating mode.
Exactly.
So our mission for this deep dive is to unpack this idea of feedback failure. We are going to look at a cold case, literally from about 290 million years ago, the Artinskian warming event. We're going to look at why the Earth's thermostat broke back then, and then the part that really kept me up last night. We're going to look at the evidence that we might be breaking it again right now.
It is a sobering comparison.
Yeah.
The key here is to understand the difference between a linear problem, like, say, walking up a hill, and a nonlinear one.
Which is like stepping off a cliff.
The Artinskian event was a cliff.
Okay, so let's start with the before picture. The article talks a lot about natural defenses. I think most people have a vague idea that, trees soak up carbon, but Above the Norm News goes pretty deep into something they call the planetary thermostat.
Yeah.
What exactly are they referring to?
They're talking about a geological process called silicate weathering. It's not as photogenic as a rainforest, but it is actually the primary reason Earth has remained habitable for billions of years. It's the long-term control knob for the climate.
I remember seeing that term in high school chemistry and immediately tuning out. But the way the article describes it, it's actually this massive planetary chemical engine.
It is. Think of it this way. Rain isn't just water. As it falls through the atmosphere, it grabs molecules of carbon dioxide. That creates a very weak carbonic acid.
So every time it rains, we're getting a tiny, tiny acid bath.
Pretty much, yeah. Now, when that slightly acidic rain lands on fresh rocks, specifically silicate rocks, and even more specifically, the dark volcanic rocks like the salt you find in the tropics, a reaction happens.
It eats away at the stone.
Right. But here is the magic trick. In the process of breaking down the rock, the chemical reaction actually grabs the CO2 out of the solution and locks it up. It turns it into dissolved ions bicarbonate, which eventually wash into the ocean.
Okay, so the carbon goes from the air to the rain to the rock and finally into the ocean.
Where marine creatures use it to build their shells, when they die, they sink, and that carbon becomes limestone on the ocean floor. It is effectively buried.
So the rocks are a sponge.
A very slow, very large sponge. But here's why it's a thermostat. Chemical reactions happen faster when it's hot. So imagine the Earth gets hit by a burst of CO2, maybe from a few volcanoes. The planet warms up.
A warmer planet usually means more evaporation, so...
More rain.
Yeah. Exactly. So now you have a hotter planet with more rain. That means the weathering process.
It accelerates. The sponge starts scrubbing carbon out of the atmosphere much faster.
It's a self-correcting system. The hotter it gets, the harder the Earth works to cool things down. That's the brake pedal the article mentioned.
Correct. It is a negative feedback loop. It stabilizes the system. Alongside forests and the oceans absorbing heat directly, this weathering engine is the ultimate safety net. Is what brings the Earth back to equilibrium after a shock.
Okay, so that's how it works on paper. That's the power steering helping us drive. But now let's go to the crime scene. 290 million years ago, the Artinskian period. Set the stage for us. What did the world look like?
It was unrecognizable compared to today. We're in the late Paleozoic Ice Age. All the major continents were smashed together into the supercontinent
Here's up in
Gondwana.
water.
And crucially, Gondwana was sitting heavily over the southern hemisphere.
And it was cold.
Very cold. There were massive ice sheets covering what is now South America, Africa, Australia, Antarctica. It's an icehouse Earth. The climate was stable, the thermostat was set to cool, and it was holding steady.
Until it wasn't. The study, led by Shisun and his team, focuses on this specific transition. They went to South China, which was tropical back then, to look at the rock layers. What did they find?
They found the fingerprints of a massive disruption. They analyzed the rock chemistry and found huge spikes in mercury.
And mercury usually means volcanoes, right?
On a geologic scale, yes. It points to the eruption of the Tarim, large igneous province, and the Panjal traps. We are not talking about a single mountain popping its top like St. Helens.
Yeah.
We are talking about flood basalt's cracks in the Earth's crust, spewing lava for thousands of years.
Okay, so there's the trigger. The gas pedal is floored. Volcanoes are dumping gigatons of CO2 into the atmosphere.
And this is where the mystery begins, because based on what we just discussed, the thermostat, the Earth should have fought back.
Right. It gets hot, it gets rainy, the weathering revs up, and the CO2 gets sucked down, the brakes kick in.
That is what the models predict should happen. But when the researchers looked at the isotopes, specifically lithium and strontium, which track weathering rates, they found something bizarre.
The brakes didn't work.
It was worse than that. As the temperature skyrocketed, the rate of weathering, the cooling power, actually dropped.
Wait, so the hotter it got, the less the Earth was able to cool itself. That's the opposite of a thermostat. That's a runaway train.
Precisely. That is feedback failure. The natural defense mechanism didn't just struggle, it collapsed.
But why? This is the part of the article that just, it blew my mind. I assumed maybe the volcanoes covered the rocks or something, but the explanation is so much more ironic.
It comes down to geography. The researchers use something called the Selene model, it's a geoclim simulation, to reconstruct the planet at that moment.
Right.
They found that the specific tropical rocks needed to soak up that carbon, the sponges, were in low-lying coastal areas.
I see where this is going. The volcanoes heat the planet. The heat melts the ice sheets on Gondwana.
And when you melt continent-sized ice sheets, sea levels rise fast.
So the rising ocean,
Right.
it flooded the rocks.
It drowned them. The ocean rose up and covered the very sponges that were supposed to save the planet.
That is just, it's tragic. The warming caused the sea level rise, and the sea level rise destroyed the mechanism to stop the warming.
It is a vicious, amplifying loop. You can't weather a rock if it's underwater. The chemical reaction stops. So at the exact moment the Earth needed maximum cooling power, its capacity to cool was cut in half.
And the article highlights that this didn't happen over millions of years. It calls it a geological instant.
Because the sink was broken, the CO2 from the volcanoes had nowhere to go. It just accumulated in the atmosphere. So the warming wasn't gradual. It was a spike. The Earth crossed a threshold and couldn't turn back.
So we went from an ice age to what? What was the aftermath?
A permanent hothouse stayed. The ice sheets on Gondwana didn't just retreat. They collapsed. We see the geological record shift completely. You go from finding glacial deposits to finding red beds, dry, oxidized, arid soils.
And the life. The article mentions the forests.
The great coal swamps, the wet, lush tropical forests that laid down so much of the coal we use today, they vanished. They were replaced by vegetation that could survive extreme heat and drought. Marine life, like the fusuline foraminifera, took a massive hit.
So the key takeaway here is that the Earth didn't just get it didn't just get a fever and recover. It broke the thermometer and moved to a new normal.
The old equilibrium was gone. Once that weathering feedback failed, the climate system found a new stability point, but it was one that was much, much hotter.
Okay, so that is the history, and it's a fascinating, if terrifying, piece of science. But the Above the Norm news article isn't just giving us a geology lesson. They are screaming from the rooftops that this is a warning for today.
And we have to pay attention to that warning. The parallels are uncomfortable. We obviously don't have the Panjal traps erupting today, but we have us.
We are the volcanoes.
In terms of carbon output, yes. We are releasing CO2 at a rate that is comparable to, and in some years faster than, those ancient volcanic events. We are flooring the gas pedal.
But do we have the drowned rock problem? Our continents are pretty high up. We aren't losing our weathering zones to the ocean yet.
We aren't losing the rocks, no. But the article makes a compelling argument that we are breaking our modern brakes in different ways.
Yeah.
We rely on two main sinks today, the ocean and the biosphere, forests and soil. And both are showing signs of failure.
Let's look at the ocean first. The article talks about stratification. What does that mean in plain English?
Think of the ocean like a giant conveyor belt. Usually cold water sinks and mixes with the deep water, taking heat and carbon down with it. It's a mixing bowl.
Mm-hmm.
But as we heat the atmosphere, we heat the surface of the
Then
ocean.
warm water floats.
Exactly. It becomes lighter, less dense. If it gets too hot, it forms a cap. It stops mixing with the cold water below. It effectively separates into layers. That's stratification.
So if it stops mixing, it stops taking the carbon down.
It stops being a sponge and starts being a lid. The ocean's ability to absorb our excess carbon drops significantly. Just like the drowned rocks in the Artinskian, the warming itself breaks the cooling mechanism.
That is not great. And then there are the forests. We always hear save the Amazon and we think about chainsaws. But the article suggests the trees might just stop working even if we don't cut them down.
This is one of the most concerning tipping points. We count on the Amazon to absorb gigatons of carbon. But heat stress and drought are changing the equation. We're seeing parts of the Amazon flipping from being carbon sinks
To becoming carbon sources.
to becoming carbon sources.
Because when a forest dries out and dies or burns, it releases all that stored carbon back into the air.
Exactly. Instead of acting as a brake, it starts acting like another foot on the gas pedal. And then you have the permafrost in the Arctic.
The sleeping giant.
It holds twice as much carbon as is currently in the atmosphere. As the planet warms, that frozen ground thaws. Microbes wake up, eat the organic matter, and release methane and CO2.
So in every single one of these cases, the ocean, the forest, the permafrost, we see the same pattern as Artsinskian. The warming weakens the defense.
That is the feedback failure. And the reason the Above the Norm news article is so alarmist is that most of our climate policies, our economic models, they don't really account for this.
We assume the brakes will always work at 100%, right? We assume if we cut emissions by X, the Earth will absorb Y.
We assume a linear relationship. We assume the Earth will help us. But this study shows that the Earth doesn't owe us that help. If we push the system too far, the Earth switches sides. It becomes an amplifier of heat, not a buffer.
It reframes the whole net zero conversation. It's not just about reaching a number on a spreadsheet. It's about not breaking the machine before we get there.
The author of the article puts it very bluntly. We are banking on natural defenses that are actively degrading. We are calculating our carbon budget, how much we can burn, based on the assumption that the oceans and forests will keep doing the heavy lifting.
But if the oceans stratify and the forests burn, that budget basically disappears.
It evaporates. If the sinks fail, our current warming forecasts are woefully optimistic. We wouldn't be looking at 2 degrees of warming. We'd be looking at a rapid acceleration toward a much hotter state, just like the Artinskian shift.
This brings me back to that idea of this switch. We tend to view climate change as this dial we can turn up and down, but looking at the geological record, it looks a lot more like a toggle switch.
Nature is full of thresholds. You can bend a stick for a long time and it just bends. But eventually you reach a point where it doesn't bend anymore. It snaps. The Artinskian warming event was a snap.
And the scary thing about a snap is that you can't unsnap it. You can't just glue the stick back together.
No. Once the Earth shifted to that greenhouse state 290 million years ago, it stayed there. The ecosystem had to completely reorganize. The species that couldn't adapt, like those coal swamp forests, simply vanished.
It really highlights the danger of playing with fire when you don't understand the building you're standing in. We're pumping carbon into a system that has a history of violent reactions.
And we are doing it at a speed that is unprecedented. The Artinskian event was fast geologically, but what we are doing today is arguably faster. We are stressing these systems, these brakes, harder than the volcanoes did.
So where does that leave us? The article ends on a pretty heavy note.
It does. It moves past the usual call for electric cars and renewable energy, which are obviously vital, and asks a deeper question. It asks us to look at the stability of the biosphere itself.
It's the realization that we aren't just fighting warming, we're fighting to keep the Earth's life support systems online.
We need to protect the sinks. We need to preserve the forests and the ocean health, not just because they are pretty or because of biodiversity, but because they are the mechanical gears keeping the climate from running away from us.
It makes you look at a tree or a patch of ocean differently. It's not just scenery, it's a piece of active machinery.
A machine that is working very hard right now to keep us safe.
The final thought from the article is the one I want to leave you all with. We need to stop asking, how hot will it get? And start asking, is the brake pedal still connected?
Because if the answer becomes no, the speed doesn't matter anymore. We need to make sure we don't sever that connection.
On that note, we're going to wrap up this deep dive. It's heavy stuff, I know, but understanding the mechanism, understanding the why is the only way to really grasp the stakes.
Absolutely. Knowledge is the first step to keeping the brakes in working order.
Thanks for listening. We'll catch you on the next one. Take care of your brakes, folks.